So long life has been a subject of great interest for this conference and for me and for the people at CARP, and I've written about it in our magazine, Zoomer Magazine. And as far as I know, up to this moment in time, there are only two surefire ways of achieving some extension in your life. And the first is severe calorie restriction. So you would have to enter into a regime where you eat considerably less than you would normally, and the occasional wag has said it may not extend your life, but it'll feel like it's extending. The other way in which to induce considerably extended life, at least in fruit flies, is to inhibit their reproduction. This was discovered by a fellow who spoke at ideacity a number of years ago, a Professor Rose. And there is some corroboration of this because I've discovered in doing some research that eunuchs living in Korea centuries ago outlived other men by a significant margin. So apparently the male sex hormone is responsible for shortening the lives of men. You might want to do something about it. On the other hand, it might be better to go for severe calorie restriction. So our next speaker is Andrew Hessel, and Andrew is a futurist of some considerable standing. He works at a fabulous company called AUTODESK. Many of you have probably heard about it. And all I can say by way of introducing him is that international megacorporations such as pharmaceuticals will spend many years, many millions, in fact, possibly billions of dollars to find a medicine which everyone can then take. Andrew has a different approach. His vision is of medicine for one person, something that's tailored to you and delivered to you in a way that you needed. Andrew Hessel, thank you.
Thank you. I guess this is in the session of longevity, so I'll try and frame it. If you want to live a long time, you're going to have to avoid cancer. Cancer is a big problem, and I have this view of cancer which is a little odd. I actually look at cancer as disk corruption. I look at cells as little computers, and they're always computing. You can't turn them off. And like any computer that's running, it tends to get a corrupted disk. The only difference is with cancer, these corrupted cells keep growing. So it creates an infection in your body with your own cells. Not a microbe, not a virus, with your own cells. And if it keeps growing, it can crash the network, which is your body, 38 trillion cells on average. Now, 100 years ago, we didn't worry so much about cancer because we really didn't live long enough. The things that killed us were microbes. A bacterial infection will kill you far faster than cancer. It'll kill you in a few days if you have a bad infection. And of course, we've got so many ways of getting infections back then, whether it was a surgery, contaminated food, et cetera, et cetera. Bacteria were everywhere. The world of medical microbiology changed radically when this compound was discovered. This is penicillin. Penicillin and its chemical cousins essentially eradicated most of the infections that killed us, virtually overnight. It took a while from 1929 to about 1945 to really ramp up production of this and other antimicrobials. But what used to kill us, suddenly, now we don't even get a day off of work with most infections. It's different with cancer. Cancer is not the difference between targeting a microbial cell, which is billions of years old, and a human cell, which is modern. It's actually trying to fight an infection with your cells and your cells that are kind of broken. Very, very short evolutionary distance. And so today we don't have anything really that selective to do that. So we carpet bomb all fast-growing cells. It's not selective at all, which is why you get that your hair falls out and you get that frailty and weakness and anemia and everything, it's because we're just killing all fast-growing cells, and many of your cells naturally grow fast. Now, we are getting some targeted medicines. Over the last 20 years, we've seen drugs like Herceptin for breast cancer or Gleevec for CML. These medicines, when they work, change the game. They're usually used with a chemotherapy, but they're so targeted that they can clean up any of these remaining cancer cells. And like penicillin, they can actually lead to cures. We all want more of these medicines, lots more of them. Patients, doctors, everybody could use these medicines. Why aren't we getting more? The challenge is the process of drug development. It's a pipeline. It takes a long time to make a new drug. On average, 10 to 15 years and over $1 billion today to make one new drug. So we all want these targeted medicines, but we're not going to get them. We really aren't, because it just takes too long. This is the most important slide in my deck. It's actually a graph of the number of new drugs made and brought to market per $1 billion invested in R&D over 60 years. Now, we all know Moore's law, faster, better, cheaper. Your computer that you buy today is much more powerful than the computer you bought a few years ago. Well, it doesn't work that way with drugs. It's exponentially negative. We spend more each year to make a drug, and it doesn't necessarily get any better. And it's still taking a long time to do it. This is a fundamental flaw in the way we make drugs. People go and protest GMO foods. Why aren't we protesting the way we make drugs with these tools and technologies? This is the number of new drugs that were approved by the US FDA last year. Not just for cancer, for all indications. 27, despite the massive investments we all make in R&D. All the donations you make, all the money your government spends, all the money invested by the pharma companies. Now, the pharma company business model isn't that hard to understand. It's really the same as Hollywood. Go out, find projects, polish them, get them past the censors, hand them over to sales and marketing, and try and get everyone in the door to buy your drug. It's the blockbuster model. And cancer drugs are kind of the big summer blockbusters. Long lineups of people, 1 in 3 people get cancer. Very low expectations of a cure, and charge a lot of money. We're not going to get the targeted drugs with this model, though. The targeted drugs are kind of like little indie art films, and they cost just as much to make. And of course, if you have a little indie art film that's only a few people are going to see, and you've invested $1 billion, you're going to have to charge a lot of money for that drug. A lot. And unfortunately, the more you charge for a drug, the harder it is to get on health insurance plans, the harder it is to pay for out-of-pocket. So it turns out that the best cancer drugs that are available today are actually used by the fewest people. And that's just got to change. It just has to change. This is fundamentally broken. I asked myself for years, could this trend be reversed? I actually worked with one of the largest biopharmas. Right here in Toronto, we had a research institute. I loved working for this place, but I realized I saw the trend line a decade ago. I wanted to change this. Now, I'm a little odd. If everyone's running that way, I'll go and see what they're running from. I also like taking things down to first principles. And I realized, well, if the world's pharma companies are all doing one thing and getting this negative slope in their production, what if we just made the anti-pharma company? What would that look like? And it would look something like this. Sorry. The slide keeps advancing for some reason. I'm not pressing the button, promise. But it would look something like this. Instead of making kind of a broad spectrum drug, it would be precisely targeted each time. The company would make precisely targeted drugs. Instead of being closed and proprietary and patenting everything, it would be really open. Instead of being for-profit, throw the money out the window. It would be non-profit, or in some way just forget about the money, find someone else to pay for it. And instead of making a mass market drug, a drug that would be sold to 2 people or 100 people or 1,000 people or 1 million people, just make it for one person, because no two cancers are identical. Remember, it's an infection of your cells in your body. Why would you ever expect two people to have an identical cancer? Now, there will be similarities, but the best drugs for cancer would be N of 1. So I built a little drug company in Canada, incorporated it in Edmonton, and it's the first co-op biotech company in the world. It's like Mountain Equipment Co-op, except that, and in fact, I kind of cloned Mountain Equipment Co-op. I just crossed out outdoor equipment and put in advanced pharmaceutical development. And instead of charging $5 for membership, I charged $20. But apart from that, it's pretty much the same. And I went out and messaging about this. This is the first open source drug company. And I started to do this just as a thought leadership exercise. Why we give all this money to research? Why don't we invest in development? And the mission was very simple: to make the best cancer medicines as fast as possible, because that's important when you have cancer, and to give them away for free. Now, free may sound a little crazy, but when you think about it, just about every service you use from Google is free. And many other companies have an underlying business model that allows them to give high-technology products away for free. Let's figure out what that model could be for drugs. And I had a special tool up my sleeve. You need some technology to do this. And I had been tracking this technology called synthetic biology, which really goes back to the previous section of DNA. Synthetic biology is one of the most powerful technologies we've ever developed on the planet. And it's basically just genetic engineering done with digital tools. Now, genetic engineering, actually manipulating the DNA molecule, we started to do that. Whoop, something just disappeared. Can we get that back? Perfect. It was actually done in labs like this for the last 40 years. This is a typical molecular biology lab. Go into any of the hospitals here, research institutes, and this is what it is. It's basically a kitchen. Liquid handling devices, complicated reagents, ingredients up on the shelves, and really scientists are cooks. It's hard to do genetic engineering in this way, which is why it takes a PhD and it's really slow and expensive to do. This is the new way of doing genetic engineering. This is essentially a laser printer for DNA. You send a digital file to it from a piece of software, and it will print out that DNA code. Now, I'm simplifying it, but that's how it works. You send it DNA, it prints the physical molecule of DNA, and you can use that DNA for programming any cell in the ecosystem. The only thing is, it's still a very crude technology in development. You can't write long chains of DNA. Now, I work for a software company, essentially the word processor, that would connect to that type of printer. Autodesk is best known for AutoCAD, designing buildings, etc., but it actually touches your lives in so many different ways, even movies with special effects. Recently, it's moved beyond software to actually working with physical bits. This is our new facility in San Francisco. Yes, I'm Canadian. Yes, I live down there now. But when you have facilities like this, where people can work with software tools and use things like 3D printers on their desk and have access to really powerful maker tools, laser cutters, 3D printers, etc., it kind of changes the whole way you think about making. And it's actually changing the whole way the company works. We're not just making software anymore, we're empowering makers. And in fact, we've been front and center with the maker movement now for basically as long as it's been around. Now, people today can go and make stuff that you just couldn't make 10 years ago because these printers are getting so powerful, whether it's 3D printers or access to outsourced manufacturing. And in my case, the 3D printer of DNA. We make a little software product called Creature, which is kind of fun. You can mash up and make creatures and 3D print them. I want to be able to do this in real life. Anyway, so we've been developing a software platform for scientists to be able to essentially program genetic material and do bio-nano things easier. It's not released to the public yet, but we've been learning a ton about this stuff. And the thing that I've been focusing on is how can I use this platform to make drugs, to make cancer drugs specifically? What can I make using these digital tools? And it turns out the answer is a virus. Now, viruses aren't really well known to most people, but we live in a sea of viruses. There's a few hundred that will hurt us, and you've heard about some plagues, Spanish flu. But most of the viruses in the world don't hurt us. And every living thing has access to a virus. And about 10 years ago, a colleague dropped on my desk a review paper on something called an oncolytic virus, cancer-breaking viruses. And here's how cancer-breaking viruses work. In fact, there's a whole library of them. They're really, really weak viruses that infect humans. They're common, they're really weak. And if they infect a normal cell, the normal cell shuts it down. It says, I know how to kill this thing. Done. But cancer cells are broken. So if it gets infected by the right oncolytic virus, it starts to grow inside the cancer cell, and it breaks the cancer cell open and releases more virus particles that can go on and infect other cancer cells. This is really cool when it works, and in fact, a lot of companies have been based on this. It's essentially giving cancer cells a cold. These are super weak viruses. Don't be afraid of them. Now, what inspired me was that 10 years ago, a group made a synthetic virus through this digital pipeline, designed on computer. Looks complicated here, but it's not. They designed it on computer. They printed the viral DNA, and then they put the viral DNA into, in this case, an E. coli cell, and it booted up the virus. And it was done in 2 weeks. Now, these are really good scientists. They're one of the top genetic engineers and a Nobel Prize winner 10 years ago. They never published how much it cost them. I decided to see if I could repeat this experiment with AUTODESK, a software company, pushing them into the world of synthetic virology. So we modeled up the virus in a much better way than it's ever been, than people typically do it. You can make it three-dimensional. We had all the 3D printers, so we printed up a 3D model of the virus. And when you can hold a virus in your hand, it's really awesome. It's like you see, it's a molecular jigsaw puzzle. It's actually like shrink-wrap software. It's like a box and then the programs inside, which is really cool. And this is my colleague Jackie Quinn, who did a lot of the legwork on this. And then we sent the DNA for that virus, really small program, about 5,000 bits, to a company called Gen9, and they printed up this DNA. And then we took that DNA, which we got comes in this format, it's just on a plate, and we booted it up in an E. coli cell. And this is a growth plate of E. coli, and everywhere you see a spot, that's where a synthetic virus booted up and started killing E. coli. So it's essentially an antibiotic. Now, the cool thing is, this is an organism made by a software company. It was also done, it started its life on my laptop. And it took 2 weeks to make it, $1,000, and no lab. And I will never, ever pay that much to make that virus again because of the cost curve in this type of technology. And of course, if I change the program, I change the drug. I can make a cancer-fighting drug, I can make a gene therapy, I can make a nanomaterial, I can make a vaccine. This process of digital virology is extremely powerful. But the thing that is most powerful is not the technology, it's the idea of N of one, making drugs for one person. For cancer, it's the most logical. It's client-focused. You always work with the person that you're going to treat. It's very small-scale manufacturing. You don't need big, giant plants for any of this. The testing is really, really easy. But more than that, you don't need phased clinical trials because you're working with one person. You can't do a big clinical trial, which means you shave off hundreds of millions of dollars and years of time in the drug development process. And I think that's what's going to change drug development. This is essentially the process. You go and sequence, you go and analyze. All that digital data informs the program and the designer of what to make. You synthesize this genome of a synthetic virus, and you can boot it up in just a few days, and you can actually test it on the biopsy that you use to get the genetic data. We're already moving to the point where we can do this on cell cultures, and I'm really making a lot of friends with veterinarians right now so we can do it in dogs. But this is the part that I love. The cost curve drops to zero with synthetic DNA so fast that this becomes a medicine we can give away for free. This is empowering makers to make more than just little plastic objects. It's empowering them to compete with the world's pharma companies. And we disappear again. This means we can change the business model. Instead of buying one drug, like one movie, maybe get a subscription to all drugs, all movies. Maybe start making your own movies. If you have cancer, pull together your own team. Make a drug for yourself. Really, this changes everything we know about drug development. And of course, we're going to need a whole new system of regulation, of security, of making sure it's not abused. But there are so many positives in exploring this path, and I hope you will join me in that exploration. Thank you.
Get a picture.
That's good. Thank you, sir.
Thank you.
That was inspiring, Andrew.
Thank you, sir.
So, ever the Canadian, can I ask you the but question? If I understand it correctly, your software, somebody's hardware, a printer, right, can come together to simplify the task of designing living things, which could include viruses, bacteria, and so on.
We've already been working with viruses for over a decade. The first synthetic bacterium was made in 2010, and an international consortium is now working on the first synthetic yeast, which we're much more familiar with, like bread and beer. So that'll be the game changer.
So
We're not going to make a human for a while.
How long will it be before some lunatic starts making bioterrorism?
Well, I've been advising the FBI and other groups on security for a while, but like 3D printing, because this whole process is digital, you can put breaks in the software, you can put breaks in the printers, you can put breaks in the education, and you can really track people better than ever before, as we know with the NSA and Snowden. So I'm not saying that accidents won't happen, it'll just be really hard to hide. It's already hard to hide. Now, there were bioweapons programs, well, there have been bioweapons programs in operation around the world, but most of them were dark. It's really hard to keep anything dark digitally. And really, rather than give over to the fear, I'd rather focus on really growing the positive applications, get things like revenues, and then apply that to making security as well.
Well, Godspeed. I hope you succeed.
Thank you, sir.